Hey everyone. After studying IUPAC naming, let's go to an interesting topic of AS level chemistry, which is isomers. So, right now, we'll be talking about isomers. If you've watched my O level video, you would remember the word iso means same and the word mer means molecule, as in monomer, dimer, or trimer. So, isomers are structures. They are basically, you can say, compounds with same molecular formula. They have the same molecular formula but a different structure. So two isomers would have same molecular formula but their molecular structure would be different. So their displayed formula, their structural formula, their condensed formula, all would be different, but in the end when you count them, they would give you the same number of carbons, hydrogens, and perhaps even other atoms. So for example, just giving you a thought, CH3, CH2, CH2, and then CH3, you would say that here you have the longest chain of 4 carbons, as in 1, 2, 3, 4. So you will call it a butane, and that is true. What if you had a branched structure with 3 carbons only, but one of them has a branch of methyl? Your longest chain would be 3 carbon because it's a continuation that matters. So you would say my longest chain has 3 carbons in it, and you will call it a propane. That is true. But since there is a branch on carbon number 2, you will call it 2-methyl propane. So these two structures have different skeletal formula, different condensed formula, different displayed formula, but their number of atoms is the same. As in when you count it, it has 4 carbons and total of 10 hydrogen. Same goes here. Now let's start talking about the categories of the isomers. Let's make a flowchart that will help us understand. So when you talk about the categories of isomers, there are 2 main categories. Number 1 is structural isomers, and the second are the stereoisomers. In today's video, we'll introduce the concept of structural isomers. So structural isomers are the ones which actually have different structures. So their structural formula, their condensed formula would be different. Stereoisomers are a little more complicated, so we'll do them in the upcoming videos. There are 3 categories of structural isomer. Let's continue our flowchart. There are 3 categories of the structural isomers. Number 1 is chain isomers. They are chain isomers. There is a position isomers, and there are functional group isomers. Let's talk about these isomers and compare them to understand how these are different and what do they mean. When you talk about chain isomers, they have different length and even positions of alkyl chains. Let me explain. For example, if you have a straight chain structure with, let's suppose, 1, 2, 3, 4, 5, 6 carbon, you will obviously call it hexane, and that is okay. But if you had a 5 carbon chain with a single branch, for example, 1, 2, 3, 4, 5. If you had a 5 carbon chain, but you had a branch on, let's suppose, carbon number 2, then you will not call it hexane, but rather you will call it 2-methyl pentane. And that is because there is a methyl branch on carbon number 2. In first case, the chain itself was 6 carbon long. But in the second case, the chain was 5 carbon long and there was a methyl on carbon number 2. So do we have any other possibility? Yes, we do. We can again have a 5 carbon main chain, as in carbon 1, 2, 3, 4, 5. And this time you can have the branch on carbon 3. The branch is still a methyl branch because it's 1 carbon branch, but your position of branch is different and still it's chain isomer. It's a 5 carbon chain, but this time it would be called 3-methyl pentane. In order for you to understand it better, I am going to write their structural formula. For hexane, for 2-methyl pentane, and then I will write it for 3-methyl pentane. While I'm writing these, I would highly recommend you guys think about the condensed formula. Hexane would be written like this: CH3, CH2. There are 4 more CH2s as in total, and then again CH3. So you can have carbon 1, 2, 3, 4, 5, 6 in a straight chain. This is your main branch. In the second structure, you have a CH3, you have a CH with a branch on carbon number 2, then carbon 3, carbon 4, carbon 5. In this case, you have 5 carbons. There is a branch on carbon number 2, so that is called 2-methyl pentane. The third structure would be 3-methyl pentane, which has a branch on carbon number 3. So there's a branch coming out of carbon number 3, CH2 and then CH3. Again, 5 carbons in a straight unbranched structure, which makes your longest chain structure. And then you have a methyl, which is carbon number 3, position 3. Position 2, position 3. This is how the chain isomers are made. In chain isomers, the concept is only difference in the structure through a change of position or like the length of the branch. So your methyl could be on 2 or 3. Your methyl could be on any other carbon. It could be an ethyl branch. When we talk about position isomers, it's all about functional group position. So the position of functional group changes. The position of functional group changes. It's not about the branch, it's not about the methyl-ethyl, it's about the functional group. Let me give you an example of position isomers. Position isomers. For example, in the skeletal formula, let's suppose you have a hexane with OH group on carbon number 2. Carbon 1, 2, 3, 4, 5, 6. Your longest chain is 6 carbon, but there is OH group on carbon number 2. So you will call it hexane 2-ol. The IUPAC name would be hexane 2-ol. What if the OH group was on carbon number 3? You are not changing the methyl position. There is no methyl here. But here, you are concerned with the position of the functional group in the 6 carbon hexane. It's a 6 carbon structure. You can see that. But here the OH group is on carbon 3. So you will call it hexane 3-ol. So do we have any other possibility? You can put your OH even more towards the right. Let's try it and let's see if it's possible or not. You could number it 1, 2, 3, 4, 5, 6. And as a random guess, you might want to put it on carbon 4, which is OH. And then you would be like, okay, sir, that is hexane 4-ol. But that is wrong. Because that does not exist. Does not exist. Why? Because if the OH is more towards the right, then the numbering should be from the right side. So numbering would not be from the left, it would be from the right side. And you would number it like this: carbon 1, 2, 3, 4, 5, 6. So it would be exactly same as hexane 3-ol. That is why I would say be careful about numbering the longest chain carbons, numbering your longest chain carbons. Now we have two more structures. Let's number these carbons, but based on the OH group, because OH group is a higher priority. We will number it from the left in both cases, as in 1, 2, 3, 4, 5, because that will make our longer chain, and OH is obviously our main functional group here. In the second structure, again we number it from the left side, as in 1, 2, 3, 4, 5. When you name them, you realize that both are pentanols, but you will call them pentenol because of the carbon-carbon double bond. So the first one is pent 3-ene-2-ol because the carbon-carbon double bond is position 3 and the alcohol is position 2. In the second structure, you will call it pent 1-ene-2-ol. So the position of the double bond is changing. Position of carbon-carbon double bond is changing. Alcohol is still in the same position. So this is how the position isomers are made. Let's go back to explore our third example, which is the functional group isomers. They have different functional groups. They have different functional groups. Let me give you a very simple example. In one of the previous videos, we talked about carbonyl compounds, which were aldehydes and ketones. So let's talk about functional group isomers. For example, if I had an aldehyde with second, third, and fourth carbon. So I had an aldehyde on carbon 1, then carbon 2, 3, 4. This is a 4-carbon aldehyde. I had another structure which is again 4-carbon, but it has the carbonyl in the middle, and thus we call it a ketone. We position it in a way that the ketone gets a smaller number, so we position it from the left side. 1, 2, 3, 4. So it would be aldehyde on one side and ketone on the other. So the first structure on the left is butanol, but the second structure would be known as butene-2-one. We position in ketones because the ketones are in the middle. So we don't need numbering for aldehyde, but we know one thing, that both have the same molecular formula. Let's count it. In the first structure, there are 4 carbons. In the second structure, also 4 carbons. In the first structure, when you count the number of hydrogens, it turns out to be 3, 4, 5, 6, 7, and 8, and only 1 oxygen. Similarly, in the second structure, the formula is still the same. So they have the same molecular formula. So in functional group isomers, the functional groups are different. So in today's video, what we talked about was the introduction of isomers. Isomers are compounds with same molecular formula but different structures. They could be structural or stereoisomers. Then we said in structural isomers, the chain ones have different methyl groups or other branches at various positions, and even their lengths different. In position isomers, we have the same functional group but on different positions. Remember, they have the same functional group but different positions. In functional group isomers, even the functional groups are different. In chain isomers, we talked about writing the skeletal and the structural formula for hexane. and methyl pentanes. In position isomers, we talked about hexanol, which was hexane 2-ol, hexane 3-ol, and we can even have hexane 1-ol. We looked at the concept that numbering of these structures is really important so that we know which structure is possible and which one is not. And then we looked at the structure of functional group isomers, of how aldehydes and ketones give the same formula but different structures. So in the next video, we'll do more examples of structural isomers. Stay tuned, guys. Thanks.